Hey YouTube, fellow math students and math teachers, DeVore here again, and today we're going to talk about a test called a water function. This can be found in the Mathematics Vision Project Math 1 Module 5 curriculum. Here we have this picture. We're talking about Andrew. Andrew walked along the water park taking photos of his family with his phone. Later he discovered his phone was missing. He drew a picture of a little map, probably on Google Maps or something, that retraced his steps to show where he had walked. See, he starts here at the entrance, he walks around a little bit, he, I guess, has to go back out to his car, he comes back and walks around the other side of the pool, and then he realizes that it's missing. Okay. If we wanted to determine Andrew's location in the park with respect to time, would his location be a function of time? Why or why not? All right, so whenever we say that something is a function of something, let's go ahead and pick that apart. What I've told you guys in the past is that we have domain and range, your inputs and your outputs. When something is written as something as a function of something, something with respect to something, here's how we take that apart. Our domain, when it's written like that, is always the second thing, whereas our range is the first thing. What this really means is that if we were to graph this, time would be on the x-axis, it would be on the horizontal axis, range would be on the vertical axis, it would be our y values. And remember also that when we're talking about functions, we want for each input, we have exactly one output. So, in order for this to be a function, there would need to be one location for each time measurement. Or he can only be in one place at one time. Last I checked, Andrew is not a teleporting time traveler. There's really no way that he can be in more than one spot at one time. So because Andrew cannot be in two places at once, this represents a function. There we go. Okay, looks like we have to sketch a couple of graphs here. You get to see my awesome graphing skills with the little draw tools. Okay, situation A, sketch a graph of the total distance Andrew walked if he walked at a constant rate the whole time. So, and this doesn't have to be pretty. Mine is certainly not going to be pretty. Let's draw something that looks like, that looks good. Alright, I'm going to draw a little bit on here. And if he's going at a constant rate, then we can say that he just keeps walking. Whoa, that is not a constant rate. Let's pretend that's a constant rate. This is what happens when Mrs. DeVore tries to draw straight lines with the trackpad. That's essentially what we're doing. If we pretend that that's straight-ish, in fact, let's make it actually straight. Something like this. There we go. Now I don't have to pretend that it's straight. There. So if he walked at a constant rate the whole time, then he's gradually just walking more and more and more and more and more. That's pretty cool. We can do that. Okay. And just remember that this down here is our time, and this is our distance right there. Situation B, sketch a graph of Andrew's distance from the entrance as a function of time. Okay, let's get our graph here again. Whoa, that is good to know that it does that. Learn something every day about this program. Okay, so let's pretend here that down here at this point right here, let's say that that's the entrance. That is, he is at the entrance. Let's look back up here though at what he's doing. He starts at the entrance and he goes, and then he heads back, and then he goes again. So we could probably represent that as he goes for a bit, and then he comes gradually back, goes back to the entrance, and then he leaves again, kind of like that. How would the graph of each situation change if Andrew stopped at the slide for a period of time? Would this change whether or not his situation is or is not a function? Let's think about how that would change situation A. In situation A, he is going at this constant rate. He's just going. If he were to stop, there would be a level period, but then he would keep going again. So, somewhere in the graph, he would have a period where the line is flat. But he would still only be in one place at one time, which would make it still a function. It would still be a function. Now, situation B, a similar kind of thing would happen. He would be stopped at the slides, I think it would probably be over here somewhere, and it would just be flat while he was stopped there. So, again, somewhere in the graph, he would have a period where the line is flat because he's not really going anywhere. But, like I said, it would still be a function because he is not a time-traveling ninja, last we checked. He cannot be in two places at once. In its most basic form, that's really what we're asking, is it possible to be in two places at once? And the answer in this case is no, unless I get some weird evidence otherwise that he's a time-traveling ninja. All right, well, that was a water function from the Mathematics Vision Project, Math 1, Module 5. Thank you so much for joining me for this video. If you like what you see, please feel free to like and subscribe and send me a message. That way I can get to know you guys a little bit better, and also you can put in some requests for videos that you would like to see me do that are not currently on my channel, and I will see what I can do to make that happen. Remember, have an awesome day, and I hope to see you guys in the next video.